Today I'm going to be going over endothermic and exothermic reactions. So if you remember, we've been talking about the law of conservation of energy. Okay, so energy cannot be created or destroyed, but it can be converted. So when we were talking about converting, like if we were rubbing our hands together, between kinetic energy is being converted to thermal energy, because as you rub your hands together, there's going to be heat produced due to friction. Okay. So we can also see the law of conservation of energy being applied whenever we're looking at chemical reactions. Okay, so in a chemical reaction, energy can be released or absorbed as either thermal energy or radiant energy. So today we're going to be focusing on the conversion of thermal energy. So if a reaction takes more energy to break than to make bonds, it's exothermic. If the reaction takes less to break than to make bonds, it's endothermic. Okay, and if you go to the homework assignment and do it's a simulation. If you click on the link and go to the simulation, it kind of walks you through the breaking and building of bonds and the energy input and output between exothermic and endothermic. Okay, so for both types of reactions, we're concerned with entropy. Okay, so entropy is just the heat contained in the system. Some people kind of refer to entropy as the chaos inside of a system. Okay, so there's two separate things in a system, or in whenever we're considering the law of conservation of energy. There's the system, which is kind of the substances that we're mixing together, and then there's the surroundings. Okay, and we're going to be looking at how entropy is changing, which is just denoted with a delta H, okay? So for the change in entropy, we have the products minus the reactants, right? And you'll notice here I have the both the endothermic and exothermic being displayed in graphs. And so we have our reactants, and then it's going to raise in energy, because this is our energy. It's going to raise in energy, and then the products end up having more energy than the reactants did. Okay, here we have our reactants. They're kind of a high energy. They're going to gain more energy, and then they're actually going to drop in energy, so that the products actually have less energy than the reactants. Okay, I just want to focus real quick on the hump that the reactants have to go through as far as energy in order for the reaction to occur. So this is just known as the activation energy. So if you were to think about if I had, like, for example, gasoline, which you know is very flammable, right? It produces a lot of heat, which is an exothermic reaction, okay? But if I just had the gasoline sitting on the table, okay, it reacts with oxygen in order to form heat, right? To catch on fire. So if I just had the gasoline sitting out on the tabletop, okay, obviously it's exposed to oxygen. It's oxygen is available to it, but it's not just spontaneously combusting. Okay, we're going to have to add energy, add heat to that gasoline to get it to ignite. Okay, that is the activation energy. So we have to input a certain amount of energy in order to make the reaction start. Okay, so all reactions need some type of energy input in order to cause it. So you'll notice that with exothermic, there's a lot more energy required to start the reaction compared to exothermic. Okay, so especially with very flammable materials, it doesn't take a lot of heat or not a very big spark in order to cause the reaction to occur, for it to combust. Okay. Whereas with endothermic, usually you need a lot more energy input to get the reaction to start, and then it'll have more energy on the opposite side. So if we're looking at the actual formulas or the chemical equations for an exothermic reaction, you'll notice I have my reactants and I have my products, but in addition to my product, I also have energy that is a part of the equation. Okay, so if I look at this one, I have my energy over here, okay, which would be my H, my enthalpy. Okay, and then I have my products over here plus energy. So the products, the actual substance, is going to have less energy because some of the energy is being released as heat. Okay, so all of this is going to equal all of this, but if we look at just specifically the products, it's going to have less because some of the energy is apart from the products. Okay, so in this case, our product number is less than the reactants, so we're going to have a negative number when it comes to the change in energy. Okay, and so once again, our reactants are going to have higher energy than our products, which will give us a negative change. And it's actually going to feel warmer. So exothermic, you could think about exiting. The energy is exiting the system and it's going to the surroundings. So whenever we touch anything that is an exothermic reaction, it'll feel warmer. Okay, so for example, like those hand warmers that you just kind of have to move around and then they start to heat up, that is an exothermic reaction. So you putting kinetic energy into it by moving around like the particles inside of the bag causes the reaction to start. That's the activation energy that allows the reaction to start occurring. Okay, endothermic, on the other hand, needs a lot more energy input into the system in order to get your products. Okay, so the amount of energy that we have, so this should actually be the opposite. I just realized, I'm sorry. The reactants should be here, the products should be up here. So we should have more energy in the products for endothermic. And so you'll see that the energy is on the reactant side. And so for this, it's actually going to feel cooler. So it's taking energy in, so endothermic inwards. So energy is being absorbed by the system. So it's going to feel colder in the surroundings. So if you were to touch a reaction that's going through endothermic, it's going to feel cool. So its change in energy is actually going to be positive because our products, like I said, this image is wrong, the products are higher than the reactants. So it's going to be a positive change in energy.